Okay. So we've been using Gnuplot to plot data files. It's very simple to get a data file plotted. That's one of the nice things about Gnuplot. It's got a nice balance of simple and flexible. So if all you want to do is see if the data that you just collected looks like it's even close to right, very simple to get it into a plot just to look at it, see if there's any pattern that you can identify. Then it's also very powerful in that you have all kinds of options that you can use to control what your plot looks like. The other really nice useful thing for Gnuplot is to plot functions. So this, especially in your guys' shoes, you guys are going to take some physics classes where you have to do some algebra and you get some function that is, the solution to some differential equation or something like that. And you want to just look at it and say, what is this function telling me? Like, what does this function look like? You can quickly plot functions in Gnuplot as well. So in order to do that, you just need to write, you basically have to, you still use the plot command, but instead of giving it a file name, you just give it an expression that it uses to calculate what the y value should be for your plot given an x value. And so you have to use the character x as your independent variable. So for example, if I wanted to plot 2x, which is just going to be a straight line with a slope of 2 that goes through the origin, I would plot 2 star x. So the star means multiplication. And then there's all kinds of functions that are implemented in Gnuplot that are very, very useful. The trig functions are all there. So if I wanted to plot sine of x, that one's pretty straightforward. You just type sine of x. E raised to the power of x, so that's the natural exponential. That is the exp function. So it's exp parentheses x if you want to do the exponent of something. Squared is the only one that's a little bit different than some other programming languages, and like sometimes calculators, like the TI calculators, when you go to square it, you use a caret, but in Gnuplot you use 2 stars. So 2 stars means raised to the power. And then if you want to do stuff like fractions, like x plus 2 over x minus 2, thing that you have to make sure that you're careful about is grouping the denominator in parentheses. Otherwise, if you don't group these in parentheses, this is going to be x plus 2 over x, all of that minus 2. Tyler, I believe you tried to write some sort of program to parse expressions like this before you found out about RPN, but this is essentially algebraic calculator type of syntax. So you can also define your own functions. So if I wanted to define a function that I could easily change later, the syntax for defining a function is name of the function you want, parentheses, the variable that it's going to take, is equal to whatever the calculation is. And then I can use that with the plot command like any other function in Gnuplot. This is a really handy feature, especially if you have functions that have a bunch of different parameters in them. You don't have to use x to define your function, but you do have to use x to plot your function. So in the second example here, I've got a function named g, which is a function of t. This is actually just the kinematic equation for something that's got an initial position of 0, an initial velocity of 2, and is accelerating at 9.8 meters per second squared. So I can use t to define my function, but when I go to plot it, the plot command only inserts values for x. So basically what the plot command is going to do is it's going to take your function, it's going to get a value for x, it's going to calculate the value for y based on the function that you give it, and then it's going to create a point for that data point. Yeah.
So with what you wrote there, you forgot to apply the 9.8 times the rest.
Oh yeah, yeah. This would be.
Would that just return an error, or would it try to graph?
No, it would return an error. So I'm missing the multiplication right here.
Yeah.
It'll complain about like an unknown symbol or something like that.
It'll do the order of operations or something like that.
Yes, like order of operations matters. So if you don't want to know if you don't know what that order is, then you need to put parentheses around stuff. All right, so let's do an example. I'm going to go into my sandbox directory.
Wow, the exponential function just comes out beautifully in the auto fit.
All right, so if I just plot x, that should be a straight line, slope of 1. And the first thing that you're going to see immediately is the difference between plotting files and plotting functions is that functions are plotted with lines by default. That's because Gnuplot is picking some X values to evaluate your function at, generating a Y value for that, and then connecting those with a line. I can give multiple functions at the same time, just like I can do multiple files. In fact, I can mix functions and files, right? I can plot data in a file, do a comma, plot a function, and have those plotted on the same graph. So all I have to do is separate things by commas. If I make a mistake, and like, for example, I just put 2x here instead of 2 times x, it's going to complain about some sort of unexpected or unrecognized token. If I try to plot something not using the x value, it's going to complain. In this case, it's going to complain about an undefined variable, right? Gnuplot does support 2-dimensional functions where you can have a function of x and y, and when you do that, it's not the plot command that you use the splot command. When you do that, y will then be interpreted as the second independent variable. Now, I don't have to have x in my expression, right? If I just plot 3, I get a flat line around 3. Doran, that's what you were doing. When you were doing that using command, you said using 1, 3, so it plotted the file, but then it plotted the function 3. So that's what that flat line was doing there. And you can basically put as many functions on the plot as you want. This is a really nice one. All of the trig functions are there. So if you have some expression that's got trig functions in it, you can easily plot it to see what it looks like. Sine and cosine are essentially the exact same function, just shifted. Cosine is shifted from sine or vice versa. These are phase shifts. If you took 212, you know that when we did alternating current circuits, we did a lot of phasors. We know that sine and cosine are out of phase by 90 degrees. EXP is the exponential function. So this is going to be an exponentially increasing function, which when you plot it on this regular scale, it basically scrunches most of the function, and then you just see the tail of it go straight up. Because this thing gets exponentially larger as you go to the right.
Yeah, when I hit 8, automatically sized it to where that the maximum value was 1 times 10 to the 50.
Yeah.
Like I don't need that quite.
If I do an exponential decay, I actually see the same thing because you can see that by default, functions are plotted over the range -10 to 10. Right. So when you're plotting files, they have a minimum and a maximum x value and a minimum and maximum y value, and it can auto scale based on those mins and those maxes. When you're plotting a function, there is no minimum and maximum because you are defining, the function can be defined from -infinity to infinity. So if you wanted to do an exponential decay, but you didn't want it to go into the negative part of the x-axis, then you would just have to set your x range to be capped at 0 on the left. Here's the function that we basically plotted out of the data file. It is a exponential decay on top of a sine wave. Yes? Tyler? It would be like a sine and a cosine and a tan. So the function name with the a in front of it for arc. This one, you can't really see the oscillations. The exponential part is so steep that you can't hardly tell that there's actually a sine wave in there. So one thing that I could do is if I just divide the x value in the exponential by 10, what that ends up doing is making the decay slower. So the function stretches out farther. Right? So this actually decays slower if I divide the argument in the exponent function by 10.
So I tried plotting a sine, a cosine, and a tangent, and they all just came out as straight lines overlapping each other at about 1.57-ish.
I'd have to look into it more.
Yeah.
It doesn't complain that they don't exist.
No.
For me,
Just
it
spits up.
says sine and cosine are undefined for all of y, but it'll plot.
Arctangent. So I would guess, let's see here. Arc cosine of 2 doesn't make any sense, right? And it's going to try to evaluate arc cosine at all x values between -10 and 10. So probably the x range is not correct for arctangent or for arc cosine and arc sine.
Really small.
So here's an exponential decay with an oscillation, and then the exponential decay part plotted on top, so you can see how the peaks of these sine waves go up and touch this exponential line here, and then they oscillate back and forth between those. Oh, I am. You can graph anything. This is what Derek requested last time, where it'd be nice if this line that was at the top was also on the bottom, so you saw some of the envelope that the sine wave oscillates in between. So I'm just going to plot that as well. So I've got oscillation between a minimum and a maximum that are given by this exponential decay. Now, that min and that max are plotted in different colors right now, which is kind of annoying. So if I wanted those to be the same, I would have to set the line type so that they were the same. The first function that I plot is going to be line type 1. That's that purple one. The second one that I plotted is this green one up here. That's going to be line type 2. And so all I've done is added line type 2 to my third plot. So this blue one will be the same color as the second function. So these should both be green. And then I've also put in a title, the title option here. So what I'm going to do here is the first one, which is the oscillation in purple, is going to have an entry in the key that says signal, and then I'm disabling the entries in the key for the other two. So the other two are just showing the envelope. I don't want to put those into the key. So now I've got a function that has my signal in purple, and then in green, it's showing the bounds, the minimum and the maximum for that function, for that signal.
My preferred is 7.
What'd you say?
My preferred line type is 7.
Your preferred line type is 7. Okay, that's good to know.
So nice and vibrant, right?
Yeah, mine is -1.
Oh, is that an option?
Much that?
It is. I think it's a dashed black line.
Oh, I think it is. Yeah, it is.
That's really good for making figures that are not going to be printed in color. -2 is not a line type.
That's great. It didn't like that.
All right, so let's get straight to scripting. I mean, it doesn't take very long before typing out all of these commands over and over again is very tedious. And especially, like, what typically will happen is you're going to make a plot, you're going to get it turned into something that you can print on paper. You're going to put it into your lab report, get your lab report printed off, walk it over to Jack or Kayvon's office, and then realize that something's missing and you need to replot it. And it's going to be much more convenient if you have all of the stuff that you use to create the plot saved somewhere instead of having to redo it all, because then that's just giving you the opportunity to make another mistake, right? Not that anybody would replot their plot, reprint their lab report, and then walk back over to the physics office to turn it in. You'd probably mark it a piece of like some pencil or something saying this should be centimeters. But if something like that happened, writing Gnuplot scripts is a really nice way to save your file. And it's really also a really good way if you're doing some sort of development where you're generating the data. It's nice to create a Gnuplot script that will plot the data, and then you can recreate the data and then immediately generate a plot to see if your data has been fixed. Like if you're either collecting data or if you're writing code that creates the data that you're going to plot, having a Gnuplot script ready is a nice quick way to get everything plotted. And go ahead.
I was just talking to myself like, oh man, this seems very convenient.
Yes, it is.
This
And
is literally what I'm doing.
if you've taken a class with Jack, typically what he does is he gives you a Gnuplot script and then he tells you run this command. The load command takes a file name, and what the load command does is it just runs every line in that file as if you typed it into the command line. It's exactly like shell scripts for the shell. It is a shell script for Gnuplot. So you can easily just write a file, then open up Gnuplot, load that file, and then it'll generate your plot all at once. So you can do the same sort of development process as you did with shell scripts, which is open up the file in one terminal, then open up Gnuplot in another terminal, edit your file, load the file in Gnuplot, see if your plot looks right. Edit your file, load the file, see if your plot looks right. So let's write a Gnuplot script that recreates this graph. So there's a sandbox. The sandbox contains a directory named data. This is the one that we've already done. It has a file named oscillations.txt. I want you to write a Gnuplot script that recreates this graph. You can see that the line type for the exponential part is not the second line type. I don't think it's 7 either, but it's
not
something
It
else.
looks to be 5.
And it's also, I'll mention this, the first part, which are these purple ones, those come from the data file and they come from column 4. You've already plotted that. This exponential decay here is not coming out of the file like it was in the last one that you did. I actually just used a function, the exponent of negative x over 50. So I did 2 of those, one in the positive side, one in the negative side to generate this. And I also changed the width of that line so that it's a little bit thicker than just a real thin line.
So do we need to generate this file like in the same directory that has like oscillations.txt in it?
Yes.
Okay.
Yep. There's a working directory associated with Gnuplot. Gnuplot, well, I mean, you can give relative path names to data files, but if you just want to give it the name of a file, you need to be in that directory. The script is going to be loaded exactly as if you typed it in by hand. So it doesn't matter where your script is at. It matters where you run your script from. That will determine what your working directory is. Let's just make this script due Monday at midnight. So work on this script Monday at midnight. We'll turn this script in. I'll have a link to upload it.
I'll turn it in Monday
Yeah.
We actually those exact colors.
Yep.
It's just gonna be like like that's just gonna be like type 5 essentially. Because I know that 2 of them are yellow, and one of them's a really ugly yellow. And it looks to be it.
He's just gonna look and see what color it is.
I have a scripts directory in here as well that has an example. So I'm going to load the plotdata.txt script, and it looks like this. The one thing that we haven't discussed yet, which you'll find in this script, is that I've got grid lines on my plot now. Right, so these little dashed grid lines, those are nice. This one has grid lines on it, so you're going to want to know how to make those. And if I go and I look at this file, it basically just contains a set of things that I would type in at the command line if I was just sitting in front of Gnuplot and trying to get this thing to plot live. So here is the file. Right up front, I've got the commands to set my labels. So I'm going to set the X label, the Y label, the title. I'm going to unset the key in this case. Right? The example that we're working on has the key in it. But if you wanted to just completely remove the key, you can just unset key, and that will remove the key from the plot. The grid, set grid here is the thing that makes that grid on the plot. And then I'm setting the X and the Y range here manually. So I'm setting the X range from -6 to 6, the Y range from -1 to 13. And then my plot command is at the very end, right?
So we don't need a shebang.
You don't need a shebang. You can put a shebang in there, and then you'd be able to run this without actually opening up Gnuplot. You could run it as an executable, and it would generate.
Would it run it through Gnuplot?
It runs it through Gnuplot. Whatever the shebang tells the shell what commands to give the file to run. That's basically what the shebang does.
Okay.
Yeah, Tyler?
We make the equations or just like show the
Yeah.
baseline.
Now it only does graphing. It doesn't solve differential equations or anything for you. One thing I want to point out here is, so if I look at, I've got on the x-axis displacement, and on the y-axis I have force, and my title is spring force versus displacement. Is that right? Spring force is the y. Yeah, okay. I got that title correct. So the first time I made this, I had the force and the displacement switched. So it was very simple to just go in here, edit the file, correct that title, then I can rerun it, generate a title that is correct. So load plot data.txt. One thing that you might notice is, like if you do something where you set your X range, every time you load a script, again, it's just as if you typed it in from the command line. So it doesn't reset everything to be as if you had just started Gnuplot. Anything that was in a script that you ran before you run another script is all still going to be there. If you need that reset, you have to explicitly reset it, or close Gnuplot, open it back up, and then run it.
Those are just a reset command.
There may be. I don't know. I never use it.
Just like grid.